Okay, this is video 2 for superposition. We are going to look at stationary wave form on a string, and the best example is a guitar. So note that all the strings have different thickness. If you've touched a guitar, you know what I'm talking about, all right? And let's see what happens when he plucks the guitar as he plays a song. So you will notice that the shapes are different and it's very nice to listen to because they have different wavelengths. So right now we're going to draw the possible wavelength on the string. And as you notice that on the string, there's a vibrator on the left. So when you pluck a guitar, when you strum a guitar, your hand becomes the vibrating device, okay? And obviously it's connected to a string with a certain tension in the wall. So the easiest one is a shape that looks like this, because the vibrator has to be a note because it's tied to the end, and the wall also will have to be a note because there's no space to move. Okay, and let's say the length of the string is L. So we know that L is lambda over 2, and lambda here will be equal to 2L. Pretty obvious because there are two notes. Okay, and if we look at the equation V equal to F lambda, this situation, which is the most simplest waveform that you can have, is known as the fundamental mode. Okay, so I'm just moving some things around. Okay, and so I label the note and the antinodes. So you can see from node to antinode, lambda over 4, node to node, lambda over 2. So L will be equal to lambda over 2, and lambda in this case is the longest, it's 2L. So the fundamental frequency, normally we call it F naught. Okay, so as I increase the frequency, the wavelength will shorten. Let's say it shortens to the point where now I can just nice fit two half waves or one single wave. In this case, my L will be equivalent to my lambda. Let's call this lambda 1. Okay, and we often call this is a different harmonics, by the way, if you learn maths, but like if you learn music. So as you can see, I've labeled the notes and antinodes, all right? And we generally call this first overtone. But as you can see, lambda divide by 2. If lambda divide by 2, F must multiply by 2. Because if you remember the equation V equal to F lambda, speed is constant. So F is inversely proportional to lambda. One side divide, the other side multiplies. This is what we call the first overtone. And F1 is double of F0. So let's say if it's 100, this will be 200 hertz. Okay, what about the next one? So the next one, we fit another half a wavelength in. So we just keep adding half a wavelength, guys, because the end to end, both ends have to be notes. Okay, so this is the next possibility. And again, now L will be equal to 3 lambda over 2 because there's 3 halves. So lambda is 2 over 3L, which is the initial value of lambda divided by 3. Okay. And oftentimes, if you look at books, they will derive a certain equation for you to use. I generally don't feel that it's necessary because you can count the wavelengths. You always remember how to count. So this is called the second overtone. If the wavelength is 1/3 of the original wavelength, then the frequency will be 3 times. So I'm just going to draw or complete the last one. All right. So we fit another lambda over 2 in. Now we will get 4 loops or 2 lambda. Okay. So right now your wavelength has been shortened 4 times because there's 2 lambda here. You can see I labeled the nodes. So 2 lambda will be equal to L. So L will be equal to, lambda will be equal to L over 2. which is 4 times shorter than 2L. So I'm not going to draw an arrow anymore, I think. And this one, we call this the third overtone. Okay, so this is an all harmonics situation. You just keep multiplying the frequency. So if wavelength divide by 4, okay, then the frequency will times 4. All right. So what is important here is not so much the equation, but the pattern. For each subsequent pattern, we add lambda over 2. We add another loop, so we add lambda over 2. And only frequencies where it allows this specific wavelength to fit. So let's say you put 3.5 f0 cannot fit, okay? It's allowed. And stationary waves are formed. If it's in between, you will not get this pattern. All right. So other frequencies, you cannot observe stationary wave. It just looks like the wave is running along the string. Okay. So this is actually the third and unwritten condition. The frequency and the wavelength have to fit certain physical constraint, which is why you tune your guitar. You adjust the length of the string. You press at different lengths. Okay, so when you adjust the length, you adjust different frequencies as well. Okay. All right. I think now we're gonna zoom out a bit, and this is what we've learned so far. We've talked about the principle of superposition, what happens when two waves meet, and we explain how when two waves meet in a certain way, especially if they're identical and traveling in the opposite direction, you get stationary wave, meaning the wavefront doesn't move. The comparison between progressive and stationary wave is a bit hard to wrap your mind around initially, but they are also frequently asked as well. And we're going to start off with the most straightforward one, which is string wave. Okay. So as you can see, right, this is actually the real world situation of the diagram that we have drawn. In the first diagram, you will see that this is the simplest one, smallest frequency, longest wavelength. So the center part is antinote. Okay, and then this one is times 2, remember? So you can see in the middle, there is a note, kind of. Again, the two ends, vibrator and retort stand, both ends have to be 0 notes, okay? So this would be the first overtone. Okay, so you notice that, hey, hang on, the loops are oscillating in the opposite direction. So if you look at the third diagram, my mouse is pointing towards all the notes, right? Okay, and you will notice that the center and the side actually oscillates alternatingly. So hence a phase relationship of 180, but the two sides go up and down at the same time. Okay, so as you can see, the frequencies are all just multiplying by 2, multiplying by 3, then multiplying by 4. I know 61 isn't exactly 60, but you know lah, experimental errors. Okay, but I think it's close enough. So if you feel that you cannot really see the wave, well then this is just some video editing where you can tell that, oh, the notes or the position of the notes. So you can see in different cases, the notes are at different places. In the first case, it's just one loop. In the second case, there's two loops with one note in the middle. In the third case, there's two notes in the middle. Okay, fourth case, 3 notes in the middle, and so on and so forth. The last one is a bit hard to see lah, unless you are there in person. Okay, but you can see now all the notes are being labeled. Green are notes and pink are antinotes. So you can see at each subsequent set or each subsequent overtone, you will have an increase in one note and one antinote. Okay, so you can see the energy is trapped between the notes. It is the most energetic. All right, so this kind of pattern, we try some examples lah. I'll see you in the next video.